Hello class. So today is going to be a fairly short lesson. We're going to be exploring vapor pressure graphs in a little bit more detail, and we're going to be exploring phase change diagrams. But I'm going to start today with a question, a really seemingly simple question, something you know, but you probably don't know why. So why is it that ice floats on water? And also, is that common? Do we often see solid phases floating on their liquid phase? Think about that for a moment. So, vapor pressure graphs. Now, on a vapor pressure graph, we are graphing the vapor pressure compared to the temperature. And keep in mind that these are the only two things we can change to make a substance boil. And remind me again, where does a substance boil? That's going to be when the vapor pressure is equal to atmospheric pressure. So with that in mind, let's do a couple more example problems with these graphs. So what temperature would ethanol need to be to boil at 60 kilopascals? So ethanol is this green line here, and it's saying if your atmospheric pressure was 60 kilopascals, what temperature would you need? So to boil, vapor pressure must equal atmospheric pressure. So our vapor pressure must be 60 or greater. At what temperature is that true for ethanol? So if we trace, I'm going to use a different color here. If we trace across to ethanol, and then we trace down to our temperature, we find that we're going to need a temperature of approximately 65 degrees Celsius for our ethanol to boil. What about another example? So at 90 kilopascals, what is the boiling point of acetic acid? So if you have an atmospheric pressure of 90 kilopascals, what is the boiling point of that acetic acid? So again, in order for our boiling to happen, our vapor pressure must equal atmospheric pressure. Thus, we're going to need 90 kilopascals. And if we trace that across to our acetic acid, and then we trace that down, we get 115, 116, something like that. So that is how you solve these problems. I could also give you a problem where we're asking the reverse. So what about if something boils at 40 degrees Celsius, what must the pressure be? So this substance X we're going to call it, it boils at 40 degrees Celsius when the pressure is reduced to 30 kilopascals. Where would the vapor pressure curve appear relative to the others? So our substance here, at 40 degrees Celsius and 30 kilopascals, which is right here, our substance boils. And remember, when it boils, vapor pressure is equal to atmospheric pressure. Therefore, it's boiling when the vapor pressure is this. So where does it lie? Well, it's going to lie somewhere between, well, it's a pretty poorly drawn line, but you get the idea. It's going to lie somewhere between chloroform and ethanol. It's going to lie somewhere between chloroform and ethanol. Now, based on this, we can actually make some assertions about the relative IMFs in these substances. So, how does the intermolecular forces of our mystery substance here compare to the IMFs of chloroform, ethanol, water, and acetic acid? Well, remember, the more volatile, right, the lower the IMF, the greater the vapor pressure will be at any given temperature. So, which of these substances has the lowest IMF? Well, that's going to be chloroform, right? Chloroform, if we were to boil at 1 atmosphere of pressure, when does it start to boil? Well, it starts to boil at 58-ish degrees, 57, something like that, or 59. And therefore, it has the lowest IMF. Which of these has the greatest IMF? Well, that's going to be acetic acid, right? Acetic acid has the highest boiling point, right? It has the lowest vapor pressure at any given temperature because it does have the strongest IMF. So, where does it fall? Well, it falls in somewhere between chloroform and ethanol in regards to its IMF, right? Ethanol has stronger intermolecular forces, whereas chloroform has weaker intermolecular forces. Okay, so vapor pressure graphs are pretty straightforward, right? I'm going to be asking you to interpret, based on a temperature, what pressure does it need to be to boil? Based on a pressure, an atmospheric pressure, what temperature would it boil at? So you need to learn how to interpret these graphs, answer questions about them, and answer questions about the relative intermolecular forces present within these substances. Now, phase change diagrams. So we learned that when we're going from a liquid to a gas, the pressure can have an impact on when that substance will boil, right? On the boiling point of that substance, because when it boils, vapor pressure must be equal to atmospheric pressure. Well, pressure also has an impact on the other phase changes as well. So here is a phase change diagram of H2O, and note that again we're plotting pressure versus temperature on these graphs. And here you can see at what pressures and temperatures your your H2O will exist as a solid, as a liquid, and as a gas. On the flip side here, we have carbon dioxide, and again, you can see where it exists as a solid, a liquid, and a gas. What do you think these black lines here represent? What do those black lines represent? Think about it. What is that? Well, if it's between liquid and solid, that is your melting point, freezing point, right? That is that phase change. If it's between liquid and gas, well, that's your boiling point, condensing point. What about if it's between a solid and a gas? That's the point at which it sublimates, right? Or that's the point at which it deposits. So the 6 phase changes are represented on this phase change diagram. Now, this does make sense. If you look here at 1 atmosphere of pressure, what happens to carbon dioxide solid, dry ice? I'm sure you've seen it in Halloween before. If I take dry ice and I put it out on the counter, what's going to happen? Well, it's going to sublimate, right? It goes directly from a solid to a gas. And if we look on our graph here, at 1 atmosphere of pressure, where does it start transitioning from a solid to a gas? Well, that's at negative 78.5 degrees Celsius. So if you're at 1 atmosphere of pressure and you put some dry ice on the counter, what temperature will it be? Well, it's going to be at negative 78.5 degrees Celsius because it's changing states. So there are some other things that we can interpret from these graphs. Let's go back to that original question. Why is it that ice floats on water? Why is that? So if we look here, as we increase the pressure here on our H2O, what phase does it favor? What phase does it favor? Well, you can see that as we increase pressure, the line goes this way, which means that we are going to favor the liquid phase. Huh. Why is that? Why would our freezing point go down as we increase pressure? If we look at carbon dioxide, on the other hand, as we increase pressure here, we notice that it favors the solid phase. Our freezing point increases as we increase pressure on carbon dioxide. Huh. Why is that? Well, if we look at the structure of water, it gives away the answer. The reason I'm talking about water is the next unit we're doing is the unit called solutions, and everything we're pretty much going to look at is going to be things dissolved in water. It is the universal solvent of our bodies and most of our planet for the most part. So when we increase pressure, why does the freezing point of water go down? Why does it favor the liquid phase? That has to do with its structure. When water forms ice, the hydrogen bonds line up in this orientation. It forms a nice crystalline structure, but you'll notice something compared to liquid, right? Liquid, the water molecules have just random bonding structures. It's not super organized. But what do you notice about the number of particles? Its density. Well, in a liquid, you have much more particles per area of volume compared to a solid. So ice is less dense than water, which is why it floats on the water, right? And this property is pretty much essential to life forming on this planet. We think that life originated at hydrothermal vents on the bottom of our ocean, but life really wouldn't have been able to develop too much if water froze from the bottom up, which most other substances will do, right? Because their solid phase is heavier, is more dense than their liquid phase. So if we had liquid CO2 and we were freezing it, it would freeze from the bottom up. So that is what is special about water, very important for life on this planet. It's one of the very few substances that will actually have a less dense solid form compared to its liquid form. Okay, so that's all for this unit. If you have questions, again, do not hesitate to ask. And we will be doing solutions next, right? So we are going to be exploring why things dissolve, how they dissolve, and again, we're going to be exploring these things at a molecular level. There's going to be an incorporation of some chemistry math back into the unit, but for the most part, it is going to be theory yet again. Right on. Have a good day, everyone.